everyone. I'm Nan. I lead our climate team here at Stripe, and we are so excited to welcome you to our first ever demo day. The intent of this format is to bring together many different parts of the ecosystem that are all collectively necessary to help early carbon removal companies succeed. And this format was largely born out of the many conversations we've had with carbon removal companies over the last year, where we have learned that it is not just customers they need. They also need to hire great people faster, as well as secure capital to operate and grow their businesses. And Stripe Climate is not playing all of these roles. We are primarily playing the role of the customer, which is why we are so excited to have such a diverse set of folks in the proverbial room today. Looking at the RSVPs, there are 200 investors, 180 researchers, 130 potential customers, many of whom are from Stripe Climate, and 170 of you are looking to join or start a carbon removal company, which I was candidly amazed by. Today, we are going to spend our time hearing from 6 exciting projects that we have just added to our carbon removal portfolio about their approaches to carbon removal, followed by a short Q&A. We'll then have a conversation with a few of our amazing experts who helped us evaluate these new projects. Our hope is that at the very least, you leave today with a better sense of what is going on in the field, and at best, leave with really specific tactical ways that you can get involved. Before diving into the projects themselves, I wanted to start by giving some visibility into how we approach carbon removal here at Stripe Climate. Ultimately, our goal here is to increase the likelihood that the world has the portfolio of carbon removal solutions needed to achieve net zero by 2050. And this likely means we will need to be removing about 10 gigatons of CO2 every year by 2050. And while some of the solutions needed to get there exist today, like planting trees and soil carbon sequestration, it is highly unlikely that these solutions by themselves are going to get us all the way there to fill that gap, in large part because we will likely run out of arable land. So we are really focused on filling that gap. And what that means in practice is we are buying carbon removal from early companies. The theory being that as an early customer, we can help accelerate promising new companies down the cost curve. And this is not a new idea, right? We've seen this play out over and over again across industries, with solar being a prime example. More tactically, we have tried to characterize that gap and what we're looking for in our carbon removal target criteria. There's a couple of things to call out here. One, we're looking for permanent solutions that, 2, don't compete with other uses of arable land and have a path to low cost, high volume carbon removal, even if they are expensive today. To evaluate these projects, we work with an incredible set of experts across disciplines, 6 of whom you are going to hear from later today. So we've been doing all of this. We did all this for the first time last year, and we just concluded our 2nd round of purchases. Some things are working really well. We were Charm Industrial's first customer, and they recently delivered our purchase months ahead of schedule. Climeworks began construction on a new facility with 80 times the capacity of their previous plant. And in addition, the average stage of company that applied this year is much earlier than compared to last year. And many of these companies actually formed within the last year. To us, this is really exciting because these are all leading indicators that our thesis is starting to work and this field is growing. On the other hand, while we did see an increase in the number of applications that met our criteria for permanence, the increase that we saw is really still nowhere near where it needs to be. To put it more bluntly, this field has a top of funnel problem, and we need to radically increase the number of promising carbon removal projects now. Otherwise, in 5 years, we are very likely going to find ourselves in a position where we have customers, but we don't actually have enough carbon removal to buy. As a result, we have adapted our funding structure this year to reflect some of these learnings. Like last year, every project is receiving a standard pre-purchase agreement, but we're also going a bit earlier and providing support to early companies through R&D grants in select cases where a grant can be uniquely accelerative for the project. We're also moving a bit later by attaching renewal purchase agreements that are conditioned on predefined milestones that we worked through to define jointly with each project. So in total, this all adds up to an $8 million commitment from Stripe Climate. 2.75 million of that is given today. 5.25 million of that is given once renewal conditions are met. and this is distributed across 6 projects. We are the first customer of 4 of them, which we are really excited about. And finally, these funds come from Stripe, as well as the more than 2,000 incredible Stripe climate businesses that are also giving a fraction of their revenue to collectively accelerate this field. With that, thank you all so much for joining today. I'm going to turn it over to Ryan, who leads procurement for Stripe Climate, and he is going to introduce the projects.
Thank you so much, Nan. We're so excited for you all to see what these projects have been working on. You'll hear from each of the 6 projects for about 5 minutes. A big principle for us is transparency. All of these and all other applications will be available on GitHub later today. Last logistical note, you can use the Q&A feature in Zoom to drop questions to each of these projects. After all the presentations, we'll ask some of the top questions to these projects, and then we'll close out the event with a Q&A with some of our experts. First up, we have Mission Zero Technologies. We're really excited about this team because they're building a new kind of electrochemical direct air capture that requires no process heat with off-the-shelf components. While still quite early and unproven at scale, we hope our support enables them to progress out of the lab and begin building larger systems. Please welcome Nicholas Chadwick, CEO of Mission Zero.
Thanks, Ryan. Well, hello, everyone. My name's Nick. I'm the CEO and co-founder of Mission Zero Technologies. And I just want to start by saying how thrilled we are to be part of this cohort this year. We sit alongside a load of amazing companies doing fantastic things in this space, and it's just an honor to be here. So Mission Zero is building a new kind of direct air capture technology that uses electricity to separate CO2 from the atmosphere and provide it as a high-grade CO2 source to be integrated with a range of sequestration pathways. So we can do really cool things to sequester CO2. We can stick it underground. We can turn it to rock deep beneath the Earth's surface. We can even turn it into products. But it's always been our analysis that the conduit, how do we connect to the atmosphere with these sequestration pathways, is one of the most important things to solve here. So this technology developing is conceptually quite simple, because maybe the term electrochemistry might invoke the idea of that. Well, I don't know what that means. So going to break it down, keep it simple as possible. So in the first step, we take CO2 from the atmosphere and we capture it using a solvent we've developed. And one of the things that we've done here is we've integrated with an off-the-shelf component technology, which has already gone down a cost curve and an experience curve over the past couple of decades. We use methodologies and tools from cooling towers, essentially, to get really high surface area transfer of CO2 from the atmosphere into our solvent. Once we've got the CO2 in the solvent, we continuously pass the solvent through another scaled off-the-shelf component technology that's currently used to provide clean drinking water to millions of people all over the world every single day. We've simply repurposed it and shown that you can use this technology to electrochemically separate the CO2 that we've captured from the solvent, realizing it as a high-grade gas instantaneously, and then also regenerate the solvent in the same process, allowing it to go back to the first stage and capture more CO2. So we continuously capture CO2 in the first step and continuously release and regenerate it in the second step. And what this does is it gets around many of the main constraints around direct air capture, in that conventional technologies are incredibly expensive, they're very inefficient, they have ties such as waste heat requirements, and for large implementations have really large land footprints. And our technology, using these off-the-shelf component technologies, using electricity, allows us to capture CO2 at a range of scales for very cheap prices. It's very energy efficient. It just uses electricity and comes in a very compact footprint, even at very high capture scales. So one of the questions that was asked of us by the Stripe team when we went through the evaluation process is, given we're invoking these off-the-shelf scaled technologies and we're simply bringing them together from different areas and integrating them with our own innovations to realize direct air capture that can be scaled quickly, is why has no one done this before? Why has it not been possible before? We think there's 3 reasons. One, lithium-ion batteries themselves have gone down a cost and experience curve themselves over the past couple of decades. And so now electrochemistry is transitioned from being a relatively niche and blue skies research activity that happens in universities to being incredibly applications focused, with something to say about everyday devices and technology. Also, 5 years ago, we were still arguing about whether renewable electricity was going to be the future of power. But that argument's won now. It's going to explode over the next 50 years. And so we should align our CDR strategies with what the future of power provision is going to be. And thirdly, climate change has caused so much water stress around the world that we've had to scale industries to solve this problem. And inadvertently, without realizing, using our technology, they've already shown us what a megaton direct air capture plant looks like. So today we've agreed a price of $319 per ton for the first 358 tons of CO2 removed from our pilot scheme, which will be happening from 2022 onwards. But we have this ambitious cost projection for where we think the total CDR cost could be in the future. And a couple of things that bring that cost down to $100 or sub $100 in the future, and that's total sequestration and capture costs. It's not just capture. Are things like CapEx innovations. These are off-the-shelf scale technologies, but bringing those down in-house will have a small gain initially, but these compound as the capture rate increases. Transitioning from first-of-a-kind to scaled nth-of-a-kind devices. And also, because the main OpEx component of our technology is just electricity, this makes sense to integrate it as much as possible with renewables. And as we get towards a megaton, gigaton scale, that effect of compounding scale and economies of scale makes our technology far more attractive to get to this $100 per ton and under. Now, what I want to do here is flip the narrative on this slide and say, well, this is the same graph, but actually to make a pitch to you into the audience to say, well, actually, we know we're not there yet. We have an ambitious vision of what the future will hold, but we need help getting there. And so there are a couple of touch points along this journey where we think you could interact with us and help us out. If you're talented and you work in this area or you want to work in this area, we'd love to hear from you. We're going to be hiring for technical and non-technical roles in the next couple of months. We'll also be raising a seed round towards the end of this year. And if you work as an investor, we'd love to hear from you. And finally, in the immediate future, we're going to be relocating our lab and office space. If you're in London and you have lab and office space going free or cheap, we'd love to hear from you as well. With a more, not immediate, but near-term future perspective, it's a conversation that has to happen soon. How do we project finance and integrate this technology and technologies like it with renewables? The renewable industry has provided a playbook of how we're going to set up these kinds of projects. But I think those conversations have to begin as soon as possible so that when we get to 2024 and onwards, we have a viable pathway forward to make it a reality. And if you're a policymaker, we'd love to hear from you and begin engaging with you as much as we can, because fundamentally, CDR and initiatives like Stripe is so important in this area, but we need to have, by 2030, a unified, codified vision of what CDR removal looks like across countries, across nations. We have to agree how we're going to judge the effectiveness of different technologies. We have to know, what the main drivers are, and that we have a level playing field for all companies and technologies working in this space, so that as a unified front, we can fight climate change effectively. So with that, I'm going to hand the mic back and just thank you for listening. In summary, we've got a really exciting technology. We have a lot to do, but fundamentally, I think you're going to play a really important part in helping us scale it. Thanks.
Thank you so much, Nick. We really appreciate you walking us through that. This was one of a few electrochemical methods that we looked at this time around, and we're quite excited about that. Next up, we have Heirloom. Heirloom's technology combines carbon mineralization with direct air capture, absorbing CO2 from the air with specially tuned minerals. There's no complicated solvents and no fans. They have a very strong scientific team, and we're really excited to see how they develop. I'm pleased to introduce Shashank Samala, CEO of Heirloom.
Thank you, Ryan and the Stripe team for having us. We're super grateful to have this opportunity to be part of this brilliant group. I'm Shashank, CEO of Heirloom. I grew up in Southeast India, where I saw firsthand impacts of climate change on people through increasing levels of cyclones and droughts that really impacted lots of folks. I'm very fortunate to be working on Heirloom. We are a direct air capture company that leverages carbon mineralization to build a low-cost, highly scalable carbon removal approach to reverse climate change. What does heirloom mean? Heirloom as a word means a precious object that we pass down from generation to generation. So in this case, it's our planet. It's in all the species and the nature living in it. Fundamental to Heirloom's technology are these low-cost minerals called carbonates. These carbonates have sequestered trillions of tons of CO2 from the atmosphere over geological timeframes. And it was very critical to maintain the carbon balance of the planet for a long time. And it really goes to show because there's trillions of tons of these minerals in Earth's crust. It shows the carbon removal scale and potential using these. So you might know these carbonates if you're familiar with the cement production. Calcium carbonate is used in that. If you're a rock climber like me, you may have used magnesium carbonate as your climbing chalk. So it's very near and dear to us. So how do we use these minerals? We call it the heirloom looping process. We start with these minerals, and the first thing we do is we bake them in a high temperature reactor. And this reactor is completely electric, driven by renewable energy. And this is where most of our costs are at scale. The first thing this reactor does, it thermally decomposes the carbonates into CO2, pure stream CO2, that we can sequester underground permanently for thousands of years. And the other thing it does, it produces oxide minerals, which are highly thirsty for CO2 coming out of the reactor. So what do we do? Well, we allow them to do exactly what they want to do, which is passively uptake CO2 without any fans or forced airflow, because it wants to react with CO2 to become stable. So that's what we allow them to do. So it takes about a year for this to naturally happen, but we've invented ways to accelerate this to about 2 weeks. So this acceleration is really important for our economics. So, then the challenge becomes, well, how do you expose these oxides to as much ambient CO2 as possible? Well, it turns out we stack thin layers of these oxides on top of each other, sort of like, white powder on cookie sheets in cafeteria tray rack configurations, both to maximize surface area contact with the air, but also to save land use. So after the carbonate, you essentially end up with what you started with, which is really great because you get to reuse these minerals over and over again, and which can sort of amortize the cost away over many cycles and also minimize mining and extraction. So what we've done here is essentially take two approaches that have drawbacks: carbon mineralization with verifiability of land use, and conventional direct air capture, which is very expensive, and combine them both together to remove those drawbacks and create a low-cost, highly permanent, and low land use, highly scalable approach, a no compromises approach, as we call it. So how much does this cost? Actually, before I jump into that, I want to cover some of the where this technology came from. So it's actually invented by some of the world's best experts in carbon mineralization, Peter Kellerman, and direct air capture, like Jennifer Wilcox. And internally, our team is made up of deep industrial automation experience. Why? Well, as you can see here, we've essentially turned, instead of using chemical synthetic sorbents and using natural carbonates, low-cost minerals instead, we've turned this from a chemical engineering, chemical plant problem into an industrial automation problem. And that's really important because we get to standardize and use a lot of the advances in agriculture, robotics, and automotive manufacturing, mining, et cetera, to standardize and leverage those technologies to make it much lower cost, faster. So our team is made up of folks from Tempo, Tesla, Plenty, and Neuro who've done this before. So how much does this cost? Well, our peer-reviewed cost models show that because we're using these low-cost minerals and off-the-shelf technologies from industrial automation, this could be as low as $50 per ton at scale. But as we all know, initial technologies will be anything but that, right? Our first cost, V0.1, very ultra small scale, unoptimized, it's going to be about a couple $1,000s per ton. And this is where Stripe is helping us come down the cost curve. Pretty quickly in phase one, we'll get this down to $250 per ton. And we'll be about hundreds of thousands of tons scale at this point. And that $250 milestone is really important because it lets us sell into compliance markets like low carbon fuel standard in California, which already allows a DAC to sell credits into. And at this stage, we'll build a small number of successively larger and simple semi-automated deployments, and most of the cost reductions will come from automation of the material handling, right? Because we're going to be moving lots and lots of this media around and manipulating it, and also from optimizing some carbon kinetics. The second phase is bringing that $250 to $100 per ton, and this is about series of progressively larger, fully automated deployments. And the cost reductions at this point will come from better design and manufacturing of racks, higher economies of scale in the high temperature reactor I showed you earlier, and also longer plant lifetimes, which lets us amortize the capex to longer timeframes. So phase 3 is really about mass production, modular deployment ready solutions. And this is where we can go much lower than 100 towards $50 per ton. And the cost reductions will come from economies of scale, low cost utilities, and cheaper financing. So what do we need in phase 1? Well, main is talent. We are looking for mechanical design engineers, software engineers, calcination lead engineers. And on the capital side, well, we are very thankful for Stripe and a couple other customers, but we need a lot more offtake partners to help us come down the cost curve initially. And on the deployment side, we're looking for folks to help us with cheap renewable energy and clear paths to permitting, especially around site location strategy for our initial deployments. Thank you so much for having us. We're incredibly fortunate and grateful for the opportunity. And good luck to all carbon removal companies working on this. Thank you.
Thanks so much, Shashank. We're really excited to see how this develops, and congrats on the launch and the announcement. Next up, we have the Future Forest Company. But just for context, we aren't purchasing forestry, as you've seen with our criteria around permanence and so on. With the Future Forest Company, we are supporting them through an enhanced weathering field trial. We're excited about this team because they're conducting this trial, which permanently stores carbonate in mineral form. Beyond the carbon they remove, we hope the papers they publish will improve the field's understanding of the ecosystem and hydrological impacts of enhanced weathering. A clearer sense of how this actually works in the field is crucial for understanding whether or not enhanced weathering could play a viable part of the world's carbon removal portfolio. And with that, please welcome Jim Mann, CEO of the Future Forest Company.
Hi, thanks, Ryan. Hi, I'm Jim, and along with Jade, I'm the founder of the Future Forest Company. And I'm not going to speak to you about trees today, as Ryan says. I'm going to be speaking with you about enhanced weathering, which is far more exciting from a carbon removal perspective. Sorry, I'm struggling with the moving on. Okay, so we're doing this up on the Isle of Mull, which is off the west coast of Scotland. You can see the site there. It's a beautiful location and a wonderful place to be working. But let me tell you a little bit more about what we're actually doing there. So rock weathering is a key element of the natural carbon cycle. It removes between 10 and 100 million metric tons of CO2 from the atmosphere every single year without us doing a thing. The way this works is that as rainfall falls through the atmosphere, it absorbs CO2, forming a weak carbonic acid. When that carbonic acid comes into contact with basic rocks, it precipitates carbonate materials. What we're doing is we're extracting rock, we're crushing the rock, and that's forming a powder that we can spread on the forest floor. Because we've increased the surface area, that means that the reaction happens quicker. And all we have to do now is wait for rain. And I can assure you on the west coast of Scotland, we don't have to wait very long before we start to get rain. There's 3 reasons why we get really excited about enhanced weathering. First of all, it's permanent. Once that carbon has been turned into carbonates, it's permanent removal, 100,000 years minimum. Secondly, it's low cost. Nature's doing this for free, so we're accelerating that natural process. We have to extract it, we have to crush it, and we have to spread it. But that's all we have to do. We believe that initially about $200 a ton, and we'll get it very quickly down to under $100 a ton as we drive the economy to scale. And thirdly, and probably most important in terms of a nature-based solution, is we don't need land for this. It's co-deployed alongside other things like agriculture. So we're not competing for land with other solutions. In terms of that scale and what that enables us to do, Professor David Beeling wrote a paper last year where he looked at how much potential this has on croplands alone. And the figure he came up with was 25 to 100 gigatons of carbon removal over the next 50 years. But that's just croplands. We think this can be deployed across croplands, across grazing land, ranch land, forestry, and timber lots. The potential here is up to 2/3 of the entire land surface of the Earth. So the potential to scale this up is absolutely massive. There are things we still need to know, though, before we can start going to that sort of scale. And that's why we're doing a large field scale trial of hundreds of hectares on the Isle of Mull. What we want to establish is, are there any co-benefits? The sort of co-benefits that have been seen in crop yield, increases in crop yield, does that occur with trees as well? We also need to establish that at this sort of scale, there are no negative impacts. We're looking at things like the ecosystem, the hydrology, and also the people who are working with rock dust on a regular basis. And then we also need to look at the optimum processes for extraction, crushing, and spreading of the rock dust, and the cost of those, and how much we can reduce that cost over time going forwards. So the site on Mull is special, and not just because of the view and the landscape, but because we have control of the entire watershed. So from the top of the hills right down to the ocean. And that gives us this very special environment where we can work at an ecosystem scale, but without anything coming onto our site. So no runoff from other people's land or anything like that, meaning we can really get some important data points that you couldn't normally get from a field trial. So in terms of where we are, well, we're very fortunate. We're delighted to be working with Stripe. It makes a huge difference to moving us forward quickly, having their support. We've also been fortunate in having successful seed raise earlier in the year. And that means we've already enhanced our team, brought on some fantastic skills, but we're still looking for more people. We'll launch our first landscape scale trial later this year, and the early data for that will lead us towards scaling up and hopefully a Series A raise. So at that point in time, we'll be interested in speaking with potential Series A funders. We're also looking to speak with more early customers, people who want to support carbon removal technologies as they come to scale. So please get in touch. And probably most importantly for us at the moment is establishing protocols and methodologies. So we're interested in finding partners to work with who are already building out these methodologies, people like Vera, VCS, Gold Standard, because we believe with the team we have and the science we have, we can help them get comfortable with the methodologies and build out the methodologies that will be needed for this to go to scale. So please do get in touch, whether you can help us with one of those, or if there's something else there that you can support us with, or you just want to find out more. Thank you.
Thank you so much, Jim. Really appreciate the overview. One sort of point of context for these folks, with many projects, we have renewal criteria based on different technical milestones. With Future Forest, one of our renewal criteria is their peer-reviewed study and results in that study indicating that this approach is worth scaling up and deploying at larger scales. So that's one of the things we're hoping to help facilitate via working with them. Next up, we have Sea Change. I'd mentioned before that we're excited about electrochemical methods. This is another new electrochemical approach. Sea Change is really interesting. They take advantage of the ocean's CO2 absorption capacity to drive the formation of stable mineral carbonates from seawater, permanently storing that absorbed carbon. Basically, use electricity to precipitate out little seashells from the water. This is an experimental electrochemical process that's yet to be demonstrated at scale, but it seems promising, and we can't wait to see how the technology develops. I'm pleased to introduce Dante Simonetti from Sea Change.
Thank you, Ryan, for the introduction. Good morning, good afternoon, good evening to everyone, depending on where you're located. My name is Dante Simonetti. I'm excited to speak to you today on behalf of Sea Change about our new technology that leverages the power of the world's oceans to affect CO2 capture. As Ryan mentioned, everyone's probably seen a seashell before in their lives. They've probably seen coral washed up on the beach before in their lives, and that's the ocean habitat's natural way of sequestering CO2. Of course, those organisms aren't thinking about sequestering CO2 when they make these shells. They're making them for their own protection. And, by extension, they're not here to capture the massive amounts of CO2 that we emit into the air. However, we can exploit electricity to mimic this process. And by doing so, we can extend that process to the entirety of the world's oceans and then build a bridge to the gigaton removal scale that we need to combat climate change. What our process does is it intakes seawater into a novel electrochemical reactor that consists of an electroactive mesh. And there's a local pH change at the water mesh interface that stimulates this precipitation of carbonates. So we're effectively forming ground up seashells on this mesh. And then the water that is depleted of the carbon and the minerals can simply be replenished through a dissolution step and sent back into the ocean, such that we have a continuous cycle where seawater becomes our reaction medium. Similarly, the solids that we form are environmentally benign. And so we can simply dispose of them either in the ocean where they would naturally exist, or on land in any sort of environmental reclamation project, or even in just some sort of environmentally benign disposal process. So what makes our process exciting? Well, we think there are 3 differentiators for our process that would make this help achieve the goals of climate change or CO2 removal in a much better manner than maybe DAC or maybe other ocean-based process. Well, the first one is permanence. So we're storing CO2 as a solid in which the CO2 will be trapped indefinitely. So this is advantageous over something that would be maybe a high pressure gas storage underground, which might have leakage issues, or even storage as maybe say a commercial commodity chemical or a fuel. The second differentiator is scale, speed, and simplicity. We have a very simple reactor that can trap massive amounts of CO2 on the order of years. Okay, so that gives us this opportunity to achieve the high rates that we need to trap CO2. And the third is low cost potential. We're exploiting a naturally concentrated reaction medium. We're using an energy efficient electrochemical process, and we're using abundant materials of construction. Okay, so that would allow us to get to a commercial sized plant very rapidly and with very low CapEx and OpEx. And so what does this path to low cost removal look like? Well, we are admittedly a young company. So as Ryan mentioned, right now we're looking at costs on the order of $1,500 a ton. That may seem high, right? But that's for a very small scale plant. What is very attractive is that we can get to sub $200 per ton values once we get to scales that are commensurate with removal of the amounts of CO2 we need to combat climate change. Something that I didn't mention earlier, but I'll mention now is that what also helps us drop this price is that we make hydrogen as a green co-product, and we can either start recovering energy from this hydrogen or start selling it on the market, and that helps us also reduce this price. Okay, so what are the drivers and what's the pathway to this? Well, the first one is getting the technology out of its birthplace in labs at UCLA and into a 1 ton per day plant. And what's going to help us do this is primarily technical work that's supported by traditional development funding and initial buyers at Stripe, which help not only give us money to underwrite this through pre-purchase agreements, but also signal to the market that they really believe that this cost curve is true and that these prices will come down in the near future. Then the second step is simply scaling up from 1 ton to several orders of magnitude higher. And this happens in 2 steps. The first step is basically getting to pre-commercial plants and pilot scale plants. Okay, and that's primarily a technical hurdle that involves us getting really good data from our smaller plants so that way we can in fact scale up rationally and scale up in an optimum fashion. Okay, but it also means that we need to find some early adopters to help us support field demonstrations. We also need to find some engineering, design, construction partners to help us build these plants of increasing size. Okay, and the next step is really going from our commercial demos out into the field, and that's really more of a business case where our drivers are finding these customers to offtake this tonnage, not only just from a buying standpoint, but also customers that are willing to own the asset, okay, to own the plant, own the CO2 that they're pulling out, okay, and also partners that help us manage regulatory and finance issues. When I say regulatory issues, not just carbon credits and carbon taxes, but also environmental rules that'll help us operate our plants rationally. And so with that, we're looking for partners, we're looking for people, R&D scientists and engineers to help us build these reactors and plants. Engineering partners, so EDC partners that'll help us do feed studies and help us build the initial plants. And then finally, customers that are going to help us with the full scale. And again, I apologize for the technical glitch, but I thank you for your interest, and hopefully I've educated everyone a little bit more about what Sea Changes has to offer.
Thank you so much, Dante. We saw a number of questions in the chat, which Dante can go address. And there's a paper they published as well that speaks a little bit more to their process, their need to realkalinize their effluent water to not throw off ocean pH. And it's a different process than the typical seashell formation, which in nature is actually a carbon source as opposed to a carbon sink. So we think this is really exciting, and we hope you follow up and learn more. Next up, we have Raul Shendure, the CEO of CarbonBuilt.
All right, good afternoon, everyone. We're really excited to be part of today's event. CarbonBuilt's technology enables the production of low cost and low carbon, but otherwise no compromise concrete. Let me just make sure we're good on the, society's foundational building material. Responsible for almost 10% of global CO2 emissions, concrete is mostly made of sand and rock. Ordinary Portland cement, which makes up 10 to 15% of the input material, is the glue that holds it all together. And while it's a great glue, it makes up around 40% of concrete's cost and over 90% of its carbon footprint. We replace it with widely available and mostly waste materials, meeting concrete's performance requirements while absorbing substantial amounts of CO2 in the curing process. This delivers two major changes to concrete's carbon footprint. The first comes from the lower embodied carbon in the materials. The second, our focus today, comes from the electricity-driven permanent removal of CO2 into a high-volume commercial product. Beyond the carbon benefits, our use of waste materials and our efficient curing process means that our technology is a source of increased profits rather than just a cost, and this drives our scalability. Absorption of carbon dioxide into precast concrete is a gigaton scale opportunity. The history of our path towards that goal is a classic tale of innovation. Our founder is a third-generation civil engineer turned UCLA professor who grew up getting into trouble on his father's construction sites. Intrigued by the carbonation kinetics of hydrated lime, he was told by his colleagues that the approach he was investigating simply could not work. And shrugging off those critiques, he and his team went deep into portions of the design space that had not been explored, leading to one of those eureka moments that every inventor dreams of. Bench experiments led to larger prototypes, and eventually, the US Department of Energy and X Prize Foundation stepped up to support our advancement to pilot scale. In the last year, at 2 demos, we've produced over 15,000 concrete blocks that meet existing ASTM standards using flue gas from power plants. We've also completed third-party performance verification, including life cycle analysis to ISO standards. Last month, we were awarded the coveted NRG COSIA Carbon X Prize, a testament to the technology's impact potential and commercial viability. Our approach can deliver unambiguously permanent gigaton scale removals without a sustained high carbon price or major leaps in technology. Our rollout involves small capital investments across a distributed infrastructure base, investments that can deliver great economic returns with today's technology. Our key challenge is overcoming the concrete industry's typically slow pace of innovation. Premium carbon removal prices help to overcome this hesitation. As comfort with the technology grows, this price can come down rapidly while still delivering great returns given the reduced commercial risk. In other words, tracking a rapidly dropping cost of capital. Now, we don't know exactly what the shape of this curve looks like, but we think the area under the curve is pretty small, something like 15 to 20,000 tons per year at less than half the price of our contract with Stripe, with a commitment period that equals the 20-year lifetime of the hardware. All in all, quite a modest investment given the benefits. Now, one of those benefits is that our approach creates space in the cost structure for integration with direct air capture, both by changing the utilization part of the process from another cost to a source of profit, and also by relaxing the concentration and humidity requirements for the direct air capture output stream. And this is certainly our vision: turnkey, integrated air to CO2 to concrete solutions for both new and existing production plants. So how do we get from here to there? We expect our first plant retrofit to be in North America, but are exploring opportunities in Europe and India in parallel. India is particularly interesting to us given the amount of production infrastructure that will be built there in the next decade. On the business model side, we'll finance our first few plants with equity, but quickly move to debt financing and then bring in licensing, particularly in geographies outside of our core. In addition, there are 4 development advances that will help enable further scale. First is product line expansion, moving from blocks to other precast products, such as pipes, segmented retaining walls, floor and wall slabs, and a whole host of others. Not as mind-blowing as whatever's on your birthday list, for sure, but we have a climate to save and concrete can be a big part of the solution. The 3 others are integration with direct air capture, which we just talked about, continuing to push up our CO2 absorption, and finally facilitating the low carbon production of hydrated lime using low-cost renewables. We can't do this without help. We are hiring, and as you can see some of our priority roles here, as well as on Stripe Climate's job board. On the financing side, if you're an early stage investor with experience in these areas listed on the right, feel free to get in touch. I'm going to close with a big thank you to our team for their truly Herculean efforts in braving COVID, ice storms, and even tornadoes in Wyoming and Alabama this year to execute on our demonstrations. And of course, to the Stripe team for inviting us to be part of this, their critically important effort to accelerate the pace of carbon removal. With that, I'll turn it back to Ryan. Thank you.
Thank you so much. And thank you everyone for listening so far. We have one more project, but just wanted to say, we spent a lot of time getting to know these teams over the last few months, and we're so grateful to have the opportunity to share them with you. So thank you all for coming. Up next, we have Running Tide. Running Tide uses the vast amount of space in the open ocean that we aren't currently really using for anything. And this team has come up with a solution that's surprisingly simple. It takes advantage of the natural sort of ability of kelp to grow and sequester carbon. And it uses simply ocean currents, buoyancy, and gravity to grow and sink kelp in the open ocean. And now I'm happy to bring up Marty Odlin from Running Tide. Thank you so much.
Hi, I'm Marty Odlin, the CEO and founder of Running Tide. We founded Running Tide 4 years ago, and our mission is to build a climate positive future by harnessing the power of the ocean. The Running Tide team combines advanced engineering and deep maritime expertise to build new climate technologies in the ocean. We've grown the team to 40 experts from a diversity of backgrounds, everything from offshore oil and gas exploration to commercial fishing, data scientists, biologists, oceanographers, and a world-class set of operators and automation engineers. Our climate solution is very simple. We grow and sink kelp in the open ocean. Our system relies mostly on energy provided by the sun, ocean currents, and gravity to put carbon on the ocean floor. So this is an acceleration of a natural carbon sink, and the simplicity makes it one of the most scalable and potentially lowest cost CDR solutions. Our system works as follows. We seed negatively buoyant kelp on a biodegradable substrate in our hatchery, and we release a seeded substrate of kelp into specific areas of the ocean that we've targeted for optimal growth and long carbon storage permanence. We call these lightweight structures microfarms because they're just really small farms. And as the microfarms drift, the kelp grows and absorbs CO2 from the ocean. After reaching maximum growth, flotation is triggered to sink. And within a matter of hours, the kelp is 1,000 meters deep in the ocean and sequestered for a minimum of 800 years, up to geologic timescales. So kelp is really good at removing CO2 from the environment, which it does 20 times faster than trees. Even better, as Ryan mentioned, it grows in the open ocean, meaning it doesn't take up land and we don't risk impermanence like we do with many terrestrial or coastal-based CDR methods. The ocean is 2/3 of the earth, and with the exception of coastlines, it is mostly unused by humans. Many people don't realize just how big the ocean is, but the size of the ocean makes this solution very scalable. The deep ocean offers natural and permanent carbon storage. There's 37,000 gigatons of carbon already there. And most oil comes from dead micro and macroalgae that sank to ancient seabeds. So on a geologic timescale, we're kind of making oil. The scaling roadmap, we've been working on this for years and have been accelerating over the past 3 years. And now we see a near vertical climb in our capacity and understanding of the systems. We started with incremental proof of concepts of like individual system components. And we're now deep into a phase of intensive research on fully functioning systems. We're learning as much as we can about the kaleidoscope of ocean currents and the dynamics of how our farms interact with the biogeochemistry of the open ocean. Ocean research will be a continued focus of the company basically forever as we continue to iterate and optimize. Initially, this drives a higher cost of deployment because our focus on research and data collection and building more robustness and nuance into our models. But concurrent to the research, we are building our megaton scale system, which we hope to deploy within 3 years. We are deep into what promises to be like a really long and difficult production ramp, where we're going to face thousands of bottlenecks and just work through them day by day. The megaton system will drive costs lower than $100 a ton. On a longer timeline, we're working on a gigaton system. But first we're working with scientists and researchers from around the world, giving them access to our data to make sure that we're not introducing externalities at these massive scales. But at the gigaton scale, we're looking at really low costs, well below $50 per ton, with further economies of scale available. So how we need help? There's 2 things we need to accomplish our goals in the short term. We want to pre-sell a megaton of carbon removal. So we encourage you to reach out to us if you have interesting leads or want to support us in a commercialization efforts. And then second, we want to hire the right team. And we have 3 job positions open right now. We have a technical program lead for a critical team. No kelp expertise necessary, but we need an excellent manager with able to manage a multidisciplinary globe spanning team. And that's obsessive about the smallest details. We need a data engineer to work with our data scientists and a massive and growing set of ocean data to build out a world-class data analytics platform. And finally, we need an agronomy lead to join our ongoing study of ocean biomass production. Once again, like no kelp expertise necessary, but we want to see like a demonstrated expertise in increasing yields from terrestrial-based plants. Thank you to Stripe and for this opportunity, and best of luck to everyone in the climate space.
Awesome. Thank you so much, Marty. And a huge thank you to everybody today for both presenting, but more importantly, for the really important work that you are all doing in this field. Okay, so to wrap up the project section, I want to share 3 very tactical things that will hopefully be helpful to folks on this call. The first is this slide. We have consolidated the needs that you heard from each project today, as well as their contact information onto this slide. So if you or somebody that you know of can help accelerate progress for these projects, please reach out to them. I will leave this up for 20 seconds for folks to take a screenshot, and maybe next year we will have a slightly fancier way of doing this. The second thing is a carbon removal job board. So we have asked all the projects in our portfolio this year to give us their top 3 most critical hires. And we've put that into another fancy Google spreadsheet, which I will drop in the Zoom chat in a minute. This will also be available from stripe.com/climate after the event. And then finally, if you don't end up finding a role at one of these companies, our team at Stripe is opening up a new role, a new strategy and operations role. We have heard from a lot of projects that they need commercialization support, but they aren't yet at the size where they can justify hiring somebody full-time for this yet. So we are going to hire that person and experiment with essentially like loaning them out to partner with each of the companies that you heard from today, as well as the companies in our portfolio from last year. This is a bit of an experiment, but I think this is a really fun and high leverage role. So if you find, if you know or are someone who'd be interested in this, please reach out. It's linked to you also from the job board. Okay, so for the final part of Demo Day, we have a conversation with our expert reviewers. We rely really heavily on these experts to help us evaluate projects, and we wanted you to hear from them directly. So with that, I will turn it back over to Ryan, who is going to lead us in that discussion and close us out.
Thanks, Nan, and thanks again, everyone, for coming and sitting this far through a Zoom panel. We know that you've never been to any of these before, and we really appreciate you taking time to spend a little time with us today. So for our expert discussion, I want to give a little bit of context. We basically solicit project applications in public. We got 26 applications this time around across a number of across a number of approaches. And we work with these experts and others that you'll meet today. They perform evaluation, they fill out review forms, which will also all be made, the review forms themselves will be made public later. And they basically help inform our decision-making. Stripe is responsible for the final purchase decisions. These experts aren't endorsers of any particular project or approach, but we can't know everything about every potential carbon removal pathway ever just on our team. So we work as much as we can throughout the field to sort of learn from their expertise and try to ensure that we're kind of pointing ourselves in the right direction to figure out what will be most accelerative. So with that, I'd like to invite our experts turn on their cameras and we can get started. We have a number of different projects across a number of different categories. We were thinking we'd have this discussion, first discuss oceans with 2 of our ocean experts, then talk about minerals, and then talk about direct air capture and electrochemistry. So we have folks from different fields that specialize in each of these areas. And I'd like to start off with oceans with Shannon and Will. So we'll kick off with Shannon. Ocean carbon removal is a relatively new area. Why do oceans have a lot of potential for carbon removal? And while there's a lot to be excited about, there's also a lot of unknowns. What are some of the key ecosystem risks or uncertainties that we should be watching out for with these projects and others?
Thanks for having me. So as we heard with running tide, we know obviously the sheer size of the ocean and the fact that there's not these land use issues involved make the ocean a really appealing place to explore for carbon drawdown. Naturally, the deep ocean stores more than an order of magnitude of carbon than soils, for example, through a process we call the biological pump. And this is biology literally taking up carbon from the atmosphere and in the surface ocean, and then that gets exported to the deep ocean, where it can stay for hundreds or thousands of years, both because of the rate of circulation of those waters, and then also much of this carbon is eventually sequestered in the ocean sediment, which is an even longer time scale of sequestration. So that permanence piece is a really strong factor in oceanic settings. And then, of course, as you mentioned, there are some uncertainties and risks. So sites should be carefully selected to avoid kind of exacerbating existing pressures on ecosystems. So, in thinking about kelp cultivation and sequestration particularly, you could have similar risks of developing kelp monocultures that you would have with other type of monoculture development, exposure to diseases and so on. And we also think of risks in transporting non-native species of kelps to different areas and potentially disrupting local ecosystems. Other questions I would just ask a project is to look into whether they're altering the composition of the phytoplankton community, and could that impact higher order species? Are you stimulating the biological activity in a way that could reduce oxygen in the subsurface ocean? And finally, I would say this is not an existing issue with the projects with running tide, for example, but with forced upwelling, which could be used as a way to draw up nutrients from depth to either stimulate phytoplankton growth or to provide nutrients for kelp farming, there's a risk of also bringing up carbon-rich deep waters and exposing that to the atmosphere, which is the opposite of what we want. So there's a lot of promise. There's some key risks to avoid. And I think most of those can be resolved by simply understanding the local dynamics of a target area in the ocean and understanding how those dynamics change along with the changing climate, and monitoring.
Yeah, thank you, Shannon. Thank you for all your sort of help throughout. I guess maybe just to your last point on potential risks of upwelling deep ocean waters, like when running tides kelp sinks, what happens to it? Like it dissolves in the deep, if they can get it below 1,000 meters, like they're hoping to, it dissolves in the deep ocean, it sediments at the bottom, it just kind of like floats around, it doesn't come up for a while. Like what's the sort of easy explanation, or where the uncertainty is for like what actually happens here?
Yeah, and that's something that's a very active area of research, to be honest. When we're thinking about kelp or macroalgae writ large, that's something that scientists are looking at as trying to understand how to count that towards the blue carbon stores. So as the kelp is sinking, as you said, it could be consumed. You could have particulate matter that breaks off before it gets to the deep ocean, but some of that we expect to dissolve and some of that carbon to dissolve and would be exported to the deep ocean. Some of that particulate matter intact would go to the deep ocean, but some of it could float off. Some of that carbon could still be available in the upper ocean. So I think that the verification and developing that piece is going to be really important moving forward, and understanding just how much is staying in the upper ocean and how much is getting exported to depth, where it has the potential to be a really massive store of carbon away from the atmosphere.
Definitely. And you can see discussion of this and upwelling in other areas in running tides, as well as other project applications that will be available on GitHub later today. Turning it over to Will to discuss governance a little bit. Oceans are international, right? They're not owned by any particular country for the most part. What's the legal framework that potential projects need to work within as they're looking at developing or scaling ocean carbon removal?
Thanks, Ryan. Yes, it is, a lot of these ocean-based CDR projects contemplate open ocean research and potential deployment. And so they necessarily involve potential impacts, both positive and negative, in the global commons. And you have a series of of treaty-based regimes that seek to balance the interests of stakeholders in the global commons and protect ecosystems. And so these projects necessarily would have to interact and look at the mandates of treaties like the Law of the Sea Convention, the London Dumping Convention, and the Convention on Biological Diversity. And in the case of these last two treaty regimes, they've both been actively involved in looking at carbon removal over the last decade, and they've started to establish standards that would be pertinent to these kind of projects. So some of the principles that would be most relevant would be the idea of transboundary consultation in cases where there are impacts either in the global commons or within exclusive economic zones of individual countries in research or deployment zones, the idea of risk assessment and whose risks are going to be pertinent, and then also the idea of risk minimization and how that would be effectuated. In cases where these projects might be coastal based or some component of it would be coastal based, you'd also have national regulatory systems that one would have to interact with, and also maybe state and local regulatory regimes. And then ideas of whether these regimes are willing to allow you to expand these projects, and whether the regimes think that these projects should be eligible for carbon credits, which may obviously be important for driving some of these projects in the future.
Yeah, definitely. Your group and some of the other public engagement groups that some of these projects are working with have been doing good work in driving clarity on this. And for context, one of our renewal criteria with Running Tide is results of a positive environmental impact assessment, sort of a clear legal framework for moving forward to larger scale deployments. That work is done sort of in a community engagement process as well as in sort of individualized legal consultations. So we've been working with folks like Will to both understand the constraints around these sorts of approaches, as well as help give guidance to projects and see how they could improve their plans to scale. To wrap up on the ocean front, Shannon, I'm curious, what are some open scientific or technical questions in the field that you'd like to see answered either via these projects, or is there anything you'd just like to see someone try?
Yeah, I think so. We already talked a little bit about the issue of what's happening with kelp as it sinks and as it's deposited. Again, that is an active area of research just to understand naturally how much of that carbon that algae is sequestering in the deep ocean. So kind of seeing demonstrations of and understanding how those mechanisms work would be very interesting. The verification piece, again, it's challenging in a dynamic system like the ocean. So I'm interested in seeing creative ways of how to address those challenges. There's a lot of technology and analytical techniques that exist in the research community that could probably be taken advantage of, but there may be other creative solutions as well. And then finally, I would just say these are still early days, of course. So the proof of concept of the core carbon removal mechanism is the target right now. But in the future, I'd just be interested to see demonstrations of systems that might combine mitigation and drawdown. So for example, if you could leverage the infrastructure of ocean-based renewable energy platforms as a platform also for carbon removal technologies as well.
Definitely. Thank you so much. And we saw sort of significantly more ocean projects this time around. We hope to fund even more this fall and next year. So if you are working on ocean carbon removal, obviously with all these concerns and context, it's an area that we're really interested in, and we hope to see more projects in this space. And thank you, Shannon and Will, for chatting here and for your help throughout. Next up, I want to talk a little bit about carbon mineralization, sometimes referred to as enhanced weathering. So to kick off with Catherine, I'm curious, we talk about this, but what does it mean to enhance weathering? Why is this relevant to carbon removal?
Right, thanks, Ryan. So enhanced weathering, also called carbon mineralization, is a natural process that some of the project presentations mentioned, but it's the natural process by which carbon dioxide is stored in geologic formations as carbonates. And most of the Earth's carbon is stored in geologic formations. And we enhance this process by trying to engineer different methods of storing carbon at faster rates, because the geologic timescale is very long, and by engineering that enhancement, we can broadly meet climate goals.
Definitely. There's just a huge amount of rocks that are very, very widely saturated with carbon. Phil, one of the big advantages of these sorts of mineral-based approaches is that the carbon storage is really quite permanent and sort of requires potentially less monitoring than some other approaches to confirm it'll stay there. Why is this?
Yeah, it's a good question, Ryan. So when we're talking about carbon mineralization, we're talking about storing CO2, as Catherine says, in new minerals called carbonate minerals, and those are essentially a lower energy form of carbon than CO2. So it's virtually impossible to reverse that on a meaningful scale. So once the carbon is stored as a carbonate mineral, it really isn't coming back.
Yeah, and this is what sort of sea change is trying to do, driving it through seawater. This is what Heirloom is using to contact the air and make these sort of stable carbonates. And this is also what Future Forest is working on with their enhanced weathering trial. So it's all different approaches to a similar process to try to just accelerate how much carbon is absorbed by these minerals. And despite these advantages that we talked about, well, we can start with Catherine on this. Carbon mineralization hasn't really been deployed at scale yet. Like we've seen from these projects, they're pretty early. In many cases, we're their first customer. The basic sort of carbonate silicate cycle science has been known for a while. Why haven't these things been deployed at wider scales? What are some of the key uncertainties that remain?
So yeah, I mean it's kind of interesting that the potential scale is enormous with the potential feedstocks of rocks, and the carbon is stable, but why hasn't it been done previously? Well, I suppose we've been thinking about this for nearly 20 years, but actually initially that was focused on capturing flue gas CO2 at high temperatures and high pressures. Now that we're starting to think about removing CO2 from the atmosphere, I think that really does change the paradigm, and we can start to think about these systems in completely new ways. So it's we're just scratching the surface with these technologies, I think. So it's exciting to see the applications in Stripe, and hope to see many more.
Definitely. We're similarly to oceans. I mean, we pick these categories to talk about because they're things we're excited to see more projects apply in. So just like with oceans, we want to see more mineralization projects. Maybe to wrap up on the mineralization front, I mean, Catherine, you work in a lab assessing and trying to enhance carbonation rates like sort of full time. I'm curious what you haven't seen someone try or what you'd like to see more of.
Yeah, definitely. Minerals that tend to be faster in this carbonation process tend to be rare in nature because they're so reactive. And so I would love to see innovative ways of engineering the carbon mineralization process for harder to react feedstocks and to kind of scale up that geologic timescale so that we can meet needs.
Definitely. Thank you both. Now I want to turn our attention a little bit to direct air capture. There's some combination here, right? Heirloom is both direct air capture and mineralization using minerals as a sorbent. But we also have seen another direct air capture company today, Mission Zero, which uses an interesting electrochemical process. Before we go into the details of different processes, I want to start off with Patricia. Just at a high level, why is it hard to take CO2 out of the air?
So I would say the main reason for that is really just the concentration of CO2. So in the air, we have about 0.04% of it. And if you compare that, for example, to flue gas, where you have about 10%, that's a factor 250 less. And it really takes then about 2 to 3 times more energy actually also to get it out. So yeah, it's hard.
Yeah, it's much easier to just not burn it than have to deal with it extremely dilute later. So Minder, sort of to that point, what are some of the different ways that we've seen people try direct air capture before, and how are these new methods we've seen today sort of different or more promising?
So far we've seen typically the solvent-based direct air capture, where the CO2 is captured with a solvent and then precipitated again. It's a mineralization process in a way, and then the CO2 is burned off. Or we've seen the solid sorbent type direct air capture, where the CO2 reacts to solid materials, and then using kind of low temperature steam and a bit of vacuum, the CO2 is released. Now, what both of these applicants and have done is basically expand on the existing solvent process. So for instance, Mission Zero, instead of burning off the CO2, which requires natural gas and it happens at high temperature, they use electrochemistry, and in that way they make it much simpler in a way, and also they can use renewable energy, which is a big benefit. And then what Heirloom does is they really innovate on the front end. So with their passive contactor, and basically they don't have to push heaps of air using blowers through a contactor anymore, but they let the air flow through their contactors themselves, and that will also save a lot of energy and thereby lower cost.
Definitely. And we've heard a bit about electrochemistry in SeaChange's case and in Mission Zero's case. What do we mean by that, and why is it kind of relevant at all? Why is an electrochemical method potentially helpful or potentially difficult compared to sort of more traditional approaches?
So maybe I can say something to that. So I think one thing that I find really exciting about it is that it's the potential to mass manufacture it and to save costs for that, right? It's similarly to battery, where we have learned to produce them very cheaply in very large quantities. And it also doesn't have moving parts. And I think that makes then maintenance cheaper. And these are really the things we need to think about when we think about scaling.
Got it. Yeah, that makes sense. And for what it's worth, particularly the electrochemical approaches we've seen today with Mission Zero and SeaChange, really, really early. They have lab and bench scale demonstrations, and we are hoping that they can support up. But scaling electrochemical processes are tricky. There's been lots of battery approaches that haven't worked out, and it's both promising but also really, really quite early. To wrap up on direct air capture, Patricia, I'm curious, what are the constraints in scaling DAC? Right, you need a lot of different things to build these systems out, and could you sort of share a little more about that?
I think first of all, we don't have some of the constraints or risks that we have in other technologies. So it's more of an engineering technology. So we're not expecting like big risks of interfering with ecosystems, for example. On the other hand, of course, the technology needs a lot of energy. So I think the scaling up renewable energy in conjunction with the direct air capture technology is really, really important, and building dedicated energy supplies. And then that also means that, of course, it really, the cost will depend on your location. So there are locations that are where we're already seeing first projects, like in Iceland, where you have a good combination of cheap renewable energy and maybe water and storage capacity all at the same place, and finding those locations and using them. That's it's not really a constraint yet, but then it really has impacts on economics.
Yeah, there's particularly easy places to build this, and then progressively harder places. And as you'd expect, a lot of companies are starting where it makes the most sense. To wrap up on this, and to both of you, is there anything in direct air capture that you'd really like to see someone try, or that you hope we purchase from next year?
Well, I mean, what I would really like to see is a first megaton scale plant, because with any engineering project, building something on a pilot scale is really exciting. It's already difficult, but then scaling that up to a megaton scale has its own challenges that need to be overcome. And only then we can see basically what the benchmark first of a kind plant cost is, and what learnings might bring in terms of cost reduction. So then we can really start to forecast where the cost might go.
For sure, yeah, couldn't agree more, and that's what we hope to help accelerate with these sorts of early purchases. With that, I think we're at time. Thank you to all of our experts, all of our project presenters, and all the Stripe team for organizing and joining today. Hopefully this was helpful. Hopefully this was interesting. We'll have our project applications all up on GitHub later today, and we expect to do another round of purchases this fall. So if you're working on a carbon removal solution, or you're an expert and you'd like to help us evaluate some of these approaches, please reach out to climate@stripe.com. We'll share out the slide with how you can help projects. We're also hiring for this role on our team. So from all of us, thank you so much for joining, and congrats to all the projects on their impressive progress. Thank you.